resistors connected in series. And now you don't talk about the charge in the resistor, you talk about the current through the resistor. And if they are connected in series, the current through the resistor that is equivalent to the resistors connected in series is equal to the current through resistor number 1, equal to the current through resistor number 2, equal to the current through resistor number 3. Essentially, it's like this, except that current is charged over time. So if you take this equation and you divide by time, it's like they're all going to have the same current. All the resistors connected in series. Notice that the formula for the resistors connected in series is of the form as the formula for capacitors connected in parallel. So these guys, they add, while these ones, they also add. Yes?
Will this information be given to us on the test, or will we have to memorize these equations?
I'll give you these equations in the test. In a quiz, I don't. But
Okay.
in a test, I do.
And then is the next test next week, or will that be moved?
Well, the next test will be, so this week I'm definitely going to cover chapter 26, and then I'm going to cover 28, and then after I finish 28, then you'll have the next test. So I'm going to jump from 26 to 28, and then I'm going to skip 27. So then we'll finish 28, and then you'll take a test. And after 28, I'm going to go back to 27, and once I finish 27, we'll jump to 29. So I may start chapter 28 this week, depending on how we do today and how we do on, yeah. So a couple of weeks.
Okay, so not next week. Mostly.
I can give it to you next
No, thank you.
Wednesday. I guess by next Wednesday, I could be giving it to you, but it's up to you.
Please no.
So number 4 will be resistors connected in parallel. And in this case, the resistance of the resistor that is equivalent to the resistors connected in parallel is given by this formula. And the voltages, when they are connected in parallel, is the same as when capacitors are connected in parallel. They're all the same. And the currents is like in this case, you just add up the currents. Okay? So notice that this formula is of the same form as this formula. So what I do is I remember the case for the resistors and then I switch it for the case of the capacitors. Notice that this one is of the same form as this one. Of the same form. So, so now what I would like to do is I'd like to discuss a particular circuit. That's what we have over here. In chapter 25, I think at the end we talk about power. I think if it's at the end of chapter 25. I think. So energy. So what are the formulas for power supplied by the source, power dissipated by a resistor? So we have the following, right? So power is defined as the rate of energy transfer, energy conversion. It's a measure of how quickly energy is being used up, supplied, converted to some other forms. So that's what power is. It's joules per second or in watts. Now, in circuits, we have that power, right? is energy over time. I can think of energy sort of like potential energy, like Q delta V, and then divided by time. But what is the rate at which charge flows through the cross-sectional area of a wire? That's just the current. So it's the current multiplied by delta V. So if you're given a battery, like a DC battery, then the power supply by the battery is just the current through the battery multiplied by the potential difference across the terminals of the battery. Now, what happens if you have resistors? If you are given resistors, you can use that the power dissipated by the resistor is the current through the resistor multiplied by the voltage across the resistor. But also from Ohm's law, if you remember Ohm's law, the master equation, right, that relates voltage to resistance, right, from Ohm's law, we had the following. That the voltage across the terminals, across the ends of the resistor, is equal to the current through the resistor multiplied by the resistance of it. So if I use that formula, this is like the master equation, and I plug it in here, then I'll get I times, and instead of the voltage, I can replace the voltage by the current multiplied by the resistance. So then I'm going to get the current times the current, so it'll be I squared times R. Or I could replace the current in this expression by the voltage divided by the resistance. And when I multiply the voltage divided by the resistance by the voltage, I'm going to get the voltage squared divided by R. So I actually have three formulas for the power dissipated by a resistor. This is similar to what we had in the case of capacitors. For the case of capacitor, we said that the energy stored in a capacitor, see if I remember this was 1/2 Q times delta V. I think that was the formula. But from the master equation for capacitors, which relates the voltage across the capacitor and the charge in each of the plates of the capacitor and the capacitance, we had that Q equals C delta V, right? So if I take this and I plug it in here, I'm going to get, well, 1/2, and then if I replace Q by this, I'm going to get C times delta V squared. But also, I could replace the voltage in this expression by Q over C. And so it would be 1/2 of Q times Q over C, so that would be Q squared over C. So we have three formulas for the energy stored in a capacitor, right? By combining, this equation with the master equation for capacitors. So same thing, if I combine this equation for power, which is energy per unit time, right, with the master equation for resistors, then I get these three other formulas. And that's what I have at the end in my notes of chapter 25. But, I wrote the formulas on that board over there for reference. What I want you to know is how to use these formulas as well, how to use this to answer questions, to solve problems. So let me go over this extra example on chapter 26. So here it is. It reads, the battery, let me move it up so that we can see the circuit. deal because we don't want to consider any resistance in this battery. In reality, in the real world, there is an internal resistance in the battery, but we'll talk about that later on. But consider a battery with no resistance. It's shown in the circuit, and the voltage across the terminals of the battery is 12 volts, like in your car. And then it's connected to these 3 resistors. It's connected to this one. 2/3 of an ohm is the resistance of that. 2 ohms is the resistance of that. 4 ohms is the resistance of that. So I asked a series of questions here. Actually, 6 questions I asked, just based on that simple circuit. So the first question was, what's the current through each of the resistors in the circuit? Another question is, B, is what's the power supplied by the battery? The power is the energy per unit time. So every second that goes by, what is the energy that is being supplied by the battery? Another question is, what is the energy, not power, supplied by the battery in 5 seconds? Well, if we know what the energy is supplied in 1 second, then we should know how much energy you should supply in 5 seconds, right? So that's just B and C are, for you to realize that there's a difference between energy and power. D, what is the power dissipated by each resistor? So how much energy is each one of these resistors dissipating in 1 second? That's the power. E, what is the total power dissipated by all the 3 resistors? And we want to show that the power dissipated by these 3 resistors is equal to the power that's supplied by the battery. Conservation of energy. Whatever the battery supplies, the resistors use up. And then, if I come with a voltmeter and I measure the voltage, the potential difference between points A and B in the circuit, what would the voltmeter read? What's the voltage between points A and B in the circuit? So, let's tackle this example. Okay. So, I just wanted to write this over here for reference, for you to see that this formula has the same form as this one, and that one has the same form as that one, right? So I am going to just erase this, because I need the board, to solve that example. So I'll just erase this, just wrote it for you to see that. And, I'll just say resistors connected in series, and over here I'll say resistors connected in parallel. And this one will be this. Now voltages will be the same. And the currents will add. And then if we have a DC battery, and I'm asked a question about the power supplied by the battery, I'll simply use this formula. But if I'm asked about resistors, what's the power dissipated by the resistors, I can use actually either of 3 formulas. I can use that, or I can use this, or I can use that. So I can use those 3 for resistors, but for batteries I'll use that one. So let me draw this circuit. Okay, so we have a DC battery here, minus plus, 12 volts. There's a resistor over here. I think I call this point B and this one point A, and this one was 2/3 of an ohm. The resistance of this is 2 ohms. And then there's another resistance like that, 4 ohms. Okay? And we have a whole lot of questions, right? What's the current through each resistor? Some questions dealing with power and energy. And the master equation, right, is that the voltage across the ends of a resistor is equal to the current through the resistor multiplied by its resistance. So, how should we tackle this problem? Is there a connection between 2 or 3 resistors that you could recognize as either being in series or in parallel, and then we can combine those 2 or maybe those 3 resistors so that we begin to simplify the circuit, pretty much like we did in the case of capacitors?
Could we say the top 2 are in series between, or not, the top 2 are in parallel, but between?
Which 2 are in parallel?
So, resistor 2 ohms and 4 ohms are run in parallel, correct? And then to find, I guess, to find everything for resistor 2/3 ohms, we could say that the top 2 are in parallel, or are in series with that one. Does that make sense? We could like condense.
Okay, so let's do one at a time. Which one should we do first? I understand what you're saying, and it's correct. But let's just do one at a time.
Just the in parallel ones.
Okay, so which is connected in parallel to what? The 2 and 4, right? Okay, so what I'll do is I'm going to draw the circuit again. So this is minus plus, this is 12 volts. I'll redraw this circuit, this resistor. And I'm going to replace this and this by 1. Right. Now, what is the resistance of this? So, how do I combine these 2 if they are connected in parallel? Then I go to my formulas over here, and I see that if they are connected in parallel, I need to add their reciprocals and then take the reciprocal of that. So I do 1 over R will be 1 over 2, right? 1 over 2 plus 1 over 4. And a half plus a quarter is 3/4, right? But remember, I gotta take the reciprocal of this, right? So the resistance of that combination is 4/3 of an ohm. So this will be 4/3 of an ohm. Yes? So now the next step is what? Then those 2 resistors are connected in?
Series.
In series. So I'll just replace them by 1 single resistor, which is equivalent to all of them, right? And when they are connected in series, how do I combine? How do I find the resistance of the resistor that's equivalent to them? Well, according to this formula, I add them up, right? So our equivalent will be 2/3 plus 4/3, and that's 6/3, which means it's 2 ohms. Now I have 1 battery with 1 resistor connected across it. So the voltage across that resistor is how many volts? What's the voltage across this resistor? 12 volts. And from my master equation, if I know any two of the three quantities, I can figure out the quantity that I'm missing. And what am I missing? If I know the voltage and the resistance, I'm missing the current, right? And that would be, well, the multiplication of actually the voltage divided by the resistance. So that's 12 volts divided by 2. So that's going to be 6 amps. So the current through this resistor, is it down the resistor or is it up the resistor? Down?
Up. Would it be up?
Why up? Why down?
Up because wouldn't the negatively charged particles be moving towards the positive terminal?
But remember the convention, right? I didn't ask which way are the electrons moving. I actually figured out which way they move and then flip the direction because by convention it was, you say that the current is in the direction that the positive charges would move if they could move. So the positive charges will move in the clockwise sense in this circuit. So we say that the current is clockwise, which in the battery, through the battery the current will be up, but in the resistor the current will be down. So that will be 2 amps, okay? And the current, what will be the current over here? 2 amps. What will be the current over here? 2 amps. What will be the current through the battery? 2 amps. What does it mean, 2 amps? It means that if I consider a cross-sectional area of this wire and I measure the charge that goes through it in 1 second, I'm going to have 2 coulombs going through that cross-sectional area of the wire in 1 second. In the next second, another 2 coulombs. In the next second, another 2 coulombs. So we first took this step to simplify the circuit, and then we took this step to simplify it further, and we're down to just 1 resistor with 1 battery. Yes?
That's a dumb question real fast. You wrote 6 amps there, but why did you write 2 amps over there?
What's that?
You had wrote 6 amps for I equivalent, but then you wrote 2 in the circuit.
Because I'm currentless.
Oh.
Thank you. So this should be 6 amps. And very soon, I would have found out that I made a mistake. Because we can check. Remember how we go back and then, so we're going to be able to check. So that's the nice thing about it. Even if I had, it's like I did this and I wrote, I don't know why, 2 amps. When I checked, I would have said, oops, something is wrong. And then I would have realized that I made a mistake. But if you see me make a mistake like that, please call it out, let me know. All right? So, this is good, that's good, that's good. All right. So, how do we check? So let's do the following, right? We know that we have this voltage and this resistance, the current through it is going to be 6 amps. Now, what are the currents through this resistor and through this resistor? I already know that the current through this one is, 6 amps, right? Actually, I gotta have 6 amps over here and I gotta have 6 amps over there. But even if I forgot that, I could say this. I could say, this resistor came from this combination. How did we say these 2 resistors are connected? In series. So how do their currents relate to one another when they are connected in series? So we go here, when resistors are connected in series, they all have the same current. So the current through the resistor that is equivalent to them will be the same as the current through the individual resistors connected in series. So since the current through this one is 6 amps, keep saying 2 amps, then this would have to be 6 amps, and this would have to be 6 amps. Yes? Now, if I know any 2 quantities, I can figure out the missing quantity, right? What am I missing? For this resistor, I know the resistance and I know the current. So what am I missing? I'm missing the voltage, right? How do I figure out the voltage? I use my master equation, and what do? I multiply the current by the resistance. So how much is 6 times 4/3? How much is? Right? So this would be 6 times 4/3. So 6 divided by 3 is 2. 2 times 4 is going to be 8 volts. Yes? And what will be the voltage across this resistor? The one at the top. I multiply 6 by 2/3. How much is 6 multiplied by 2/3? Well, 6 divided by 3 is 2. 2 times 2 is 4. So this should be 4 volts. Now, did I do that right? Let's check. These two resistors are connected in series. How do their voltages relate to one another when they are connected in series? Well, the sum of the two voltages must equal the voltage of the resistor that's equivalent to them. So it's 4 volts plus 8 volts equal to 12 volts. Then it's good. I'll get rid of this. Okay? Get rid of that, get rid of that. So I know that the voltage across this resistor is 4 volts. The current is 6 amps. This resistor is the same as this one, right? So the current through it is 6 amps. The current here was 6 amps. Now, how will this current split to then go through these two resistors? Right? So now I need to remember that this resistor here, this one at the top, is this one. But remember that we said that these two connected in parallel combine to give me this one. But I have full information about this resistor. I know the voltage and I know the current through that combination. So, these two are connected, how did we say? In parallel. What do they have that's the same for both of them and also the same as this one? The same voltage. When they are connected in parallel, when resistors are connected in parallel, they all have the same voltage. And since I know the voltage of this to be 8 volts, then the voltage across this resistor here will also be 8 volts. And across this one will also be 8 volts. Yes? And if I know two quantities, I can figure out the missing quantity. What am I missing? The current, right? So the current through this resistor and the current through this resistor. So how do I find the current? If I know, so I go to my master equation, right? If I know the voltage and I know the resistance, I should be able to figure out the current. So how do I find the current? I take the voltage and I divide by the resistance. So how much is 8 divided by 2? And how much is 8 divided by 4? Now, did I do this right? Let me check. I just found their current, right? And they are connected in parallel. How do their currents relate to one another when they are connected in parallel? Well, for resistors connected in parallel, the currents must add up to the value equal to the current through the resistor that's equivalent to them. So, is 4 plus 2 the same as 6? And the answer is yes. So, I guess that answers the first question in this example. The first question was calculate the current in each of the 3 resistors. So the current through this resistor is 6 amps, the current through this one is 2 amps, and the current through that one is, it's 4 amps for this one, and the current through this one is 2 amps. That's the answer to the first question. Any questions?
On the exam, do you want us to just draw that, or do you want us to box answer it?
So I'll give you the circuit, and you'll have to figure it out. By drawing it, it helps.
Okay, do you want to box the answer at the end, because I know there's a lot of numbers.
Yeah, and you should draw big. And you can actually write, current through the 2/3 ohm resistor, 6 amps, to the right. Current through the 2 ohm resistor, 4 amps down in the circuit, right? And the current through the 4 ohm resistor, actually that was 4 amps, the other one is 2 amps down. You can then box that. Yes?
On the most simplified drawing, when we have the resistor in between points A and B there, are we allowed to do that? Because we're technically moving the other resistor past it? Or is that just not representative of it anymore?
No, actually this is A, right? Actually this shouldn't be there.
Okay.
This one is still B, but that one is not A. Good point. And I'll come back to that when we answer one of these other questions. But this one is A, B. That one, this is correct over here, but shouldn't be there. Yes. Other questions? Comments? Yeah, this is a very simple circuit. So make sure that you understand, because we're gonna, in the homework you'll do more complicated ones, and so you have to be able to understand this one before you move on, do the simple ones before you do the harder ones. Yes?
I was just wondering, for the voltage for the 2/3 ohm resistor, it stays the same, right? Because the flow is
So this resistor is the same as this one, so it should be 4 volts.
right.
So 6 multiplied by 2/3, so the voltage across this, right, that should be 4 volts. And the voltage across this one is 8, and the voltage across that is 8.
And then that stays the same because there's no, it doesn't split. There's no change. The flow is just like straight through it.
What do you mean? So remember what this voltage means. It means that if the potential here, suppose the potential here is 50 volts. Suppose it's 50 volts. What will be the potential here? Same thing as the case of the capacitor. That should move along. If you don't go across anything, then it's the same potential. So that will be 50 volts. What will be the potential here?
$72 volts.
How much?
72 volts. Or I mean 62 volts. Forgot how to
62
math.
volts. Right? This means that this is the difference between these two potentials. And this one being longer, positive, and this one being shorter, this is of the higher potential. Because the answer could have also been 38. But this is higher potential than this. Because this was drawn longer, right? That's why we say that that's plus and that's minus. So that's 62 volts. So this is here is 62 volts. So this here is 62 volts. Now, what's the potential over here? And notice that this is the direction of the current.
58 volts.
So what should it be?
58 volts.
58 volts. Because the voltage across this is 4 volts. This means, the 4 volts means that the difference in potentials across the ends of the resistor is 4 volts. So if this happens to be 62, this happens to be 58 volts, right? And what is the direction of the electric field through that resistor? Set up by this battery.
To the right?
To the right, yeah, from positive to negative. So the electric field points this way. So if you move in the same direction as the electric field, the potential drops. And that's why it's 58 as opposed to 66 volts. And the potential at this point is 58 volts. The potential at this point is 58 volts. What's the potential over here? What does it mean that when you say that the voltage across this resistor is 8 volts?
50 volts.
It means that this difference is 8.
Right.
But would this be 66 or 50 volts?
50 volts.
And the electric field in the circuit there, right, is this way. In the direction of the current. That's why I guess it helps to draw the current, right, as if the positive charges go that way, because that will be the direction of the electric field. So therefore this is 50 volts. And this is 50 volts. And that's 50 volts. And this is 50 volts. and this is 50 volts, right? But what does it mean that the voltage across this is 8 volts? It means this will be what? The current is down, so the electric field is down. So what should this be? 58 volts. 58 volts. I think one of the questions was, what's the voltage between points A and B, right? Well, the voltage at A, or the potential at A minus the potential at B would be 58 minus 50. It's the 8 volts. And I just chose 50 randomly. I could have chosen any other number, and the answer is the same. The voltage across that resistor, or between points A and B, is 8 volts. Okay. Question? Can I erase this? Can I erase this? Okay. So, one of the next question, so the first question was find the current in each resistor, or through each resistor. The next question asks, calculate the power supply by the battery. What is the power supply by the battery? So what formula should I use?
P equals I delta V.
Right, I should use this one. The current through the battery multiplied by the voltage across the battery, right? What is the current through the battery? I see 6 amps. And what is the voltage across the battery? I see 12 volts. So this is 72. And what are the units of power? It's joules per second or watts, right? That's the power supply by the battery. What does that mean? That means that in 1 second, the battery will supply 72 joules of energy. In the next second, another 72 joules of energy. In the next second, another 72 joules of energy. In the next second, another 72 joules of energy. That's what it means, right? That's the power supply by the battery. Battery is the source of the energy here. Next question. What is the energy supplied by the battery in 5 seconds? What's the energy supplied by the battery in 5 seconds? How do I find that answer?
Multiply.
Yeah, if I know how much it supplies in 1 second, which is the power, well, in 5 seconds, you just multiply that by 5, right? So it's like this formula, power equals energy over time. Right? People like to memorize formulas. So it's the power multiplied by the time. So this is 72 joules per second times the 5 seconds, if you want to see it like this, right? And so 5 times 2 is what, 10? Is that 360 joules?
Yeah.
In 5 seconds, right? It's basically, do you know what the difference is between energy and power? A lot of people think they're the same thing. They're not the same thing. D, calculate the power dissipated by each resistor. Well, I have 3 resistors, 2/3 of an ohm, 2 ohms, 4 ohms. So what is the power dissipated by the 2/3 of an ohm resistor? What's the power dissipated by the 2 ohm resistor? And what is the power dissipated by the 4 ohm resistor? That's what we're being asked. So, how many resistors do we have? 3. How many formulas could I use to figure out the power supplied by the resistors, dissipated by the resistors? 3. So how about I use this formula for one of them, this one for the other one, and this one for the other one, so none of their formulas feel neglected. So I'll use this. I'll use this, and I'll use this. So they don't complain and say, oh, you like those formulas more than you like me. So, well, for the resistor with resistance 2/3 of an ohm, if I use the current times the voltage, what is the current through this resistor? 6. And what is the voltage across it?
4 volts.
4. So 6 times 4. And the answer is 24 watts. I'll just use that notation. What about the for the 2 ohm resistor? What is the current through it? For the 2 ohm, what was the current? 4 amps. And what was the resistance? 2. So this would be 4, and I have to square that thing times 2. So that should be 32 watts. And what about the 4 ohm resistor? I'm going to use voltage squared divided by the resistance. So what is the voltage across the 4 ohm resistor? 8. And what is the resistance? 4. So this would be 8 squared divided by 4. That would be 64 divided by 4. That looks like 16 to me. Is that right?
Yep.
Now, here's the cute part about it. What is the sum of the powers dissipated by the resistors? Well, 24 watts by one of them, plus 32 watts by the other one, plus 16 watts by the other one. And that's every second, right? This resistor, the 2/3 ohm resistor, dissipates 24 joules of energy in 1 second. In that same second, this other resistor of 2 ohms dissipates 32 joules of energy. And in that same second, the other resistor, the third resistor of 4 ohms, dissipates 16. So how much is 24 plus 32 plus 16? So that looks to me like 12 carry 1, 3, 6, 72. Isn't that nice? Precisely what the battery supplies. Conservation of energy at its best. So if I could, if I just could use this notation, right? So if you say, how come the current to this resistor has to be 4 amps, and the current to this one has to be 6 amps, and the current to that one has to be 2 amps? Well, because energy is conserved. If they're not those values, energy is not going to be conserved. So the battery is supplying the energy. The battery uses through some chemical process, it converts chemical energy in the battery to electrical energy. And the resistor takes that electrical energy and converts it, dissipates it to usually thermal energy. And the resistors get hot when there's a current through them. So they dissipate that energy, they convert the electrical energy, part of, each one, its amount, right? Converted to thermal energy. So that, precisely what the battery supplies in electrical energy, the resistors convert to thermal energy. Precisely the same amount in every second that goes by. Now, is that a good thing? Well, sometimes it is. Sometimes you want conversion of electromagnetic energy into thermal energy. Right? If you're going to toast bread, you have your toaster, you connect it to the wall outlet, you put your bread in there, you lower the lever. When you lower the lever, you close the circuit. And there's going to be a current. If you look inside where the slice of bread is, if you look inside next to the bread, you'll see these wires that go like this. And they'll begin to glow as the wires get hot. So the electrical energy, right, that was supplied to those wires by the wall outlet gets converted to thermal energy, which toasts your bread, and it makes it taste, better. So in some cases, you want that. Or to dry your hair, right? With a hair dryer. So there's a little circuit that with a switch for on off. You connect it to the wall outlet. There's a resistor in there. When you turn it on, there's an electric current in the circuit, and the resistor gets hot. And right behind it is a fan, and the fan goes zzz, and it blows air. And then that air goes past the hot resistor, and thermal energy flows from the hot resistor to the air, and then the air takes that energy, that thermal energy, and you deliver it to your hair to dry your hair before you go outside or whatever it is, So, there are cases when that is the application that you want. You want thermal energy, and you get it by converting electrical energy into thermal energy, and resistors can be used to do that. I think there was another question, E. Actually, two more questions. Oh no, E was, what is the total power dissipated by all three resistors, and show that it is equal to the power supplied by the battery. So I guess that was this. This is equal to power supplied by the battery. And then F asks, what is the voltage between point A and B? So the approach that we will use is this. We want to know what is the voltage, the potential difference between A and B. So the way that I do it is like this. I look at this expression and I see the minus sign, right? And I see B to the right of the minus sign. So what I do is I take a trip. So I start at this point. So I'm going to start at point B in the circuit. I'm going to start over here. And I'm going to take a trip. And I'm going to move towards point A. And I'll stop when I get to point A. And this is me going from point B to point A, and I'm going to stop over here. Now, how can I get from point B to point A? Actually, I have three choices. I can go, that's me, right? I can go this way, or I can go this way, or I can go this way. How about I take all three paths and show that the potential difference is going to be the same? How about I do that? Okay, so I'm going to go straight up first. So here, this is me over here. And I go, What will be the potential difference when I go from this point to this point? What's the potential difference across that resistor? 8 volts. Did I go up in potential or did I go down in potential? Because I need to write either a +8 or a -8.
Up in potential?
Up in potential because the electric field, because the electric field through the resistor is down, and that's the direction of the current, right? So if you go in the opposite direction as the current, the potential gets bigger because you'll be going in the opposite direction as the electric field. So as I go from point B to point A straight up, the potential difference is 8, and I'm moving in the opposite direction to the current. So it's +8. So the answer is +8. 8 volts. Or, what if instead I take this other path, where I start over here, at this point in the circuit, and I go to the right, and I don't go across, if I don't go across anything, I don't write anything down. And then when I go across this resistor, what is the voltage across this resistor when I go from here to there? Another 8 volts, right? And was it a rise or a drop in potential?
An increase because you're moving against
The
the electric
current through
field.
here is down, right? So that's the direction of the electric field. So if I go against the electric field, the potential gets bigger. Remember, that's actually in chapter 23, I think, when we wrote dV is minus E dot dr, right? So we said if you move in the same direction as the electric field, the potential gets smaller. So that means that if you go in the opposite direction of electric field, the potential gets bigger. So as I go here, I go across this resistor, so the potential difference is 8, and then boom, I'm done. So that's another 8 volts. Now, or I could also take the other path. What if I take the other path from point B to point A? So I start over here and I go this way, right? So nothing happens. What will be the potential difference as I go from this negative terminal to this positive terminal? By how much does the potential change? By plus 12. I'm going from low to high. So it increases by 12. And then I continue my trip. And then I continue. And what will be the potential difference across this resistor? It'll be 4. Now, am I moving in the same direction as the current or opposite direction to the current? And the current is in the direction of the electric field.
Same direction as the current.
Same. So will the potential get smaller or bigger?
Smaller.
Smaller by 4. So I put a minus 4. And 12 minus 4 is the same answer as for the other paths. So the potential difference between points A and B is 8 volts. Which path do you take? I'll choose the easiest one, the one that has less terms, so I don't have to calculate so many things. Yes?
Sorry, in a test, do we need to write down 3 A's like that, or should we only write one?
I mean, this one is so obvious, but I mean, I would probably write instead of this one, but this one I would say, 2 times 4, which equals 8. Or you can say through the